Then our first speaker for this session, Aerodynamics 2, is Mojtaba Khairi from Concordia University in Montreal. So please, the floor is yours.
Thank you very much, Roland. So I'm, as Roland mentioned, my name is Mojtaba Khairi, and I'm associate professor at Concordia University in Montreal. So one of few representatives from North America. So today I'm going to share some results from aerodynamic shape optimizations for airfoils and wings, and my focus today would be mostly on 2D sections or airfoils. So the primary objective is, of course, to develop a fast, reliable aerodynamic shape optimization framework. As I said, 2D and 3D, and for particularly crosswind kites. So here I'm showing the overall process. So we begin with a first generation, initial generation based on the limits of the design space, and we pass it to an airfoil parameterization method. So here we use IGP, which is improved geometric parameterization. So it's quite a recent, method, 2018. So the implementation in MATLAB, and which basically generates some text files that can be read or execute basically X-file. So we use X-file for aerodynamic solver because it's fast. And then once the results are obtained, they will be passed to a post-processor, again in MATLAB, and then to the optimizer based on the genetic algorithm. So I give a little bit of details about a few of these boxes, and this is how the process goes on and on. So just a quick note is that in the post-processor we just identify the linear range of CL alpha because that's what we want to use. But what is IGP? If I want to quickly touch on that is as I said, it's a 2018 paper. So the crux of this method is that they try to decouple camber and thickness, and as a result to get lower number of variables for shape generation. So in total, we have 8 variables. So when you compare it with more maybe established methods like CST, we normally need to have 17 to 21 variables to have something reliable. Or parsec, we need 11. So the idea of using IGP is that this reduction of the number of variables potentially can decrease the optimization runtime, which indeed it happens. So we tested one case where we used CST versus IGP, and we got 3 times faster results. So as a result, we're going to use IGP. Now, in terms of genetic algorithm or optimization methods, so here are typical parameters we used, in the simulations. So in terms of objective functions, we need to have 2 conflicting objective functions. One is, of course, related to power. The other one, we chose the maximum thickness. Again, looking at Kroon 2018, one of the studies at TU Delft. Also, there are several studies by Roland's students. So we looked all those, and we picked one based on or inspired by Lloyd's equation. So the idea here is that we are not optimizing for a single value of CL. We are optimizing or getting optimal shapes for a range of values of CL, because that would be more representative of operational condition. If you have gust, if you have turbulence, you have a range of values of CL, but then we have weight functions, those W values that I'm going to present. But because we need to define them in minimization framework, we have like 1000 over FP. So that basically minimize that means that we maximize FP, and that 1000 is to get a nice resolution when we look at the Pareto fronts. And the other one is maximum thickness. From a structural point of view, it's important to have thicker airfoils, but aerodynamically that's basically not useful. So it's conflicting, again, because we need to have minimization. We minimize the negative sign of FT, or maximum thickness. Now, going to results, so we call what we have as a baseline, which means that just purely 2D airfoils, no other effects. This is the range of CL 0.5 to 1.2 we consider, again, following Kroon's, and the weight functions just to penalize lower values of CL and improve results on higher values of CL. So on the left, you see Pareto front, where we have a second objective function versus the first objective function. So because it's minimization, the points that are closer for any given value of thickness, the points closer to the left, they are better in terms of power generation. So as you see, it's a good distribution over different values of thickness from maybe less than 10% over 45%. So for thinner airfoils, we agree with Kroon's results. By the way, Kroon used CST, and they used Airfoil for aerodynamic solution. So we have two differences. We use X-foil and we use IGP. Now, when we look at the thicker airfoils, we see that the orange has a little bit of better edge, or we have got better solutions compared to Kroon's. So I'm going to discuss about what could be the reason for that. On the right-hand side, I'm showing the shapes. They are more look like maybe wind turbine, conventional wind turbines airfoils. Now, the first hypothesis for the difference was we are using different aerodynamic solvers. So they are using Airfoil, which was for us a black box because we don't have access to it. It's TU-Delft, I think, the development or addition to X-foil. So we thought maybe that's the reason. So what we did was we looked at Kroon's study. We looked at their airfoils. We picked two, like 35%, 40% thickness airfoils, and we ran both X-foil and Airfoil. And as you see, the green and red, so green be Airfoil results, and red would be X-foil results. And we found that for the linear range of CL alpha, where we do not expect any major flow separation, they agree and they are identical. But wherever we have flow separation beyond those limits, they do not agree, which again makes sense based on indications we had from Airfoil. So then our hypothesis about the flow solver difference didn't come true. So and we linked it to different airfoil parameterization methods because they use CST, and perhaps that resulted in different designs. So we moved forward. We said, okay, now how much of these results are reliable when we compare it with higher fidelity results? For example, if we have RAN solutions. So here I'm showing a comparison between X-foil and CFD, specifically RANs, using K omega SST turbulence model. So we see that for some range of angle of attack, they agree very well. But as angle of attack increases, of course, see big differences in both CL and CD. So CL being on the top left and CD would be on the top right. And then underneath you see what I call it aerodynamic efficiency, but it's basically CL cube over CD square. So we see order of magnitude differences in prediction. So that's, again, showing that X-foil results are overestimating the potential power. So in terms of pressure coefficient and in terms of streamlines, again, we can see why this difference is coming. Of course, is because of the flow separation. You can identify it in both CP plots, and from streamlines you see as we increase the angle of attack, especially at 6 degrees, we have large flow separation close to the trailing edge. And that, again, indicates why we have differences. Now, moving on to a system that I call it modified system 1, because now we would like to inject a little bit of 3D, three-dimensional effects, like, for example, aspect ratio, because that's related to induced drag. So basically, we modify a little bit of the table to get more competitive airfoils, because now we have added drag. So with this change, we go to Pareto front. Again, on the top, we have the Pareto front. The blue is showing the baseline system, and the other colors show different aspect ratio from 4 to 20. So as we increase aspect ratio, we expect that the Pareto front reaches or gets close to the baseline system, which is happening. In terms of shapes, you see 3 families of shapes depending on the thickness, so 20%, 30%, and 40%. Our general observation is that the optimization is pushing the design more towards cusp-shaped airfoils. Especially at 20%, you see this round and sharpie, trailing edge. So that's our interpretation in terms of the design. So in terms of comparison, again, with CFD here, we see the trend is very similar between X-foil and CFD. However, again, the values on both CL and CD differ. They are not agreeing very much. But interestingly, in terms of at which angle of attack we get the maximum aerodynamic efficiency, they are close, about, let's say, 2-3 degrees, as we see from the green one and the red one at the bottom row. In terms of CP or pressure coefficient and in terms of streamlines, again, we see wherever we have major flow separation, the results would deviate. That's our expectation. Again, the green on the pressure coefficient shows CFD results, while the other one, the red one, is X-foil results. So we can identify some flat regions where it indicates, we have flow separation, and we can confirm exactly from streamlines where, we get flow separation. Now, moving to the last system, or modified system 2, here we include the effect of tether drag by introducing area ratio. So it's basically the ratio of the projected area of the tether divided by the area of the kite. And again, I'm using the same table as I used, for aspect ratio. And we get also a Pareto front. We try different values of area ratio that correspond to different scales of the system. So some of them, especially the high values, are a little bit hypothetical. They are really large. But we wanted just to see how design is changing. So again, we have different families of airfoils, 22%, 30%, 40%. Our interpretation by looking at all these shapes is that, especially at 22%, you see that close to trailing edge, we have kind of a broken trailing edge. So it looks like a flap. So it means that, we need some sort of a flap to reach those high values of CL. So we think, the design is, or the optimization pushes the design towards the multi-element airfoil, which is in line with what Makani, concluded. If we want to have really high values of CL, we need to go for at least 2-element, airfoils. So again, in terms of comparison with CFD, we see for some ranges of angle of attack, we have exact, and identical results. However, as we have flow separation, they tend to be completely different. In terms of, again, CP, for low values of angle of attacks, like -3 degrees, 0 degrees, we see that even the CP distribution is very similar. But as we go to 3 degrees, we see that the CP distribution becomes completely different. So to summarize my talk, we found that the use of IGP can potentially result into better solutions, what we call it better solutions, and also reduce the computational time. So that was important for us. The use of X-foil in optimization framework can be justified if we do not encounter flow separation, if we do not go to really high values of angle of attack or very low values of angle of attack. But we have to keep in mind that, there would be anyway an overestimation of the aerodynamic efficiency or power. So as I said, if we consider the effect of aspect ratio, again, the way that we did it, it seems that the optimization pushes for designs with cusp-shaped airfoils, while if we include the effect of tether drag or by using area ratio, it seems that the design is pushed towards multi-element airfoils, which again in lines with some of the works also on several element airfoils for Crosswind kite power system. Thank you very much.
Thank you very much. Yes, we have a few questions. No, but it will not be transmitted.
I'm concerned. It's working? Okay. The one thing I'm concerned about is that when you play with X-foil, there is this N parameter that you can set anywhere between 0.5 and 9, and that changes everything in terms of the separation and also the CL max and things like that. So, and then there is also the Reynolds number. So the N parameter is a big player in X-foil. I don't know about R-foil. And then there is also the Reynolds number. So how did you decide on those, and how sensitive are your results to changing those parameters?
It's a very good point. In terms of N critical, I think we chose 9 based on the recommendation mentioned in Airfoil documentation. So that's absolutely true. I mean, it basically determines the separation point, that plays with N critical. In terms of Reynolds number, I didn't mention, but it's at 6 million. We just chose it based on typical, a small, maybe a scale kites, and also because Kroon's study was at 6 million. But you're absolutely right. I don't remember exactly the sensitivity results with N critical, but we looked into what would be the case, because it says if you have a dirty flow, if you have like a wind tunnel that is very nice, so you have to like play with N critical. So depending on, I think we chose N equal to 9, which is kind of a calm, wind tunnel test. I think that was the reason to consider that. But of course, we use the viscous version, not the inviscid version, because that's another thing.
And define the region, and define the start of the transition.
Yes, exactly.
Florian.
Yeah, Florian here from Kitecraft. Once you include the tether drag, you see that the optimizer wants to get a really high lift coefficient, which is beyond that what a single element airfoil can do. So that's why also single element airfoils are actually useless for a rigid kite. So what I would encourage you is to really go to multi-element, because this is a actual research job. We did a lot of airfoil optimizations at Kitecraft and at TUM. But still, this is not closed yet, and I would like to have is a family of airfoils with different CL max and different thickness. So I want to have this family in this direction and in this direction, because then we can use that in our optimization. And if you would have then airfoils which are optimal in that sense, so for a certain CL, certain thickness, minimize the drag. So you don't have to count the tether drag or anything else, because you just look at the airfoil. Then we can use that for our optimization and also for the structural optimization, because the thickness is also important then. So it's definitely important, and I encourage you to do that. But go to multi-element airfoils for sure, and also do wind tunnel tests to check it out. And also such features like a gurney flap is interesting, because this is what we also saw in the wind tunnel and what the optimizer told us, take a gurney flap.
Thank you very much for the great points. I mean, I'm aware of your work, Florian, and I know that you have looked into maybe 4 or 5 elements, so that's very inspiring. We just wanted to stick to one element just to see what we're gonna get. That's a starting point, but as you said, the solution for getting high lifts is, of course, go to multi-element. And I think one of Roland's students looked into 2-element optimization. I remember from last AWEC, he was presenting on that. So that was just the starting point, just a foot, in the field. But of course, that's the way to go if you want to have really high values of CL. Thanks.
Thank you. Are there any other questions? In the meantime, I have a remark. I was able to track down the source code of Airfoil in our section, because it was developed there, and we are now discussing to put it on GitHub. And my goal is to have it openly accessible as a free software for everyone to use. And so far nobody objected, so with a bit of luck, I can implement that.
Because we had a hard time, we had to look into airfoils from Kroon's thesis. My student had to digitize it and then smooth it, because if you have really rough, airfoil, you got completely different results. So he had to do that and then digitize, the CL alpha, which is not a hard thing to do. But if we had Airfoil, we could just do it, right away with our own airfoils. So that would be a great, I think, contribution. Thanks.
Yes, so, and that's an invitation for everyone who wants to use it. If it's not online available within, let's say, a month, contact me, and then I try to speed up the process.
And maybe we are also planning, to have this as open source. The framework in MATLAB, might be useful, for playing at least for now, but we're going to do it hopefully in a few months, so it would be shared with the community.
Great, thanks. Are there any other questions? Here, Mac.
Do I have to press something? Okay. We also, Mac from the DTU, and DTU has, or from from when Risø, which is a part of DTU now, was not DTU, we designed airfoils for wind turbines using X-foil. And the tricks we used there to get something where the X-foil calculations agreed with CFD was that we also use a mix of free transition and a forced transition models to get them roughness insensitive, because some of the early versions we did was very roughness sensitive because we ran only free transition, which is not really what is happening in real life. And actually other constraints to make sure that some of the cases that X-foil have a hard time really predicting doesn't happen. So that's might be an idea to look into, because you had a nice agreement in some part of the linear region, and then X-foil was completely off.
Yeah.
And so that's what we did. A lot of work around to actually make sure that that the optimization only is allowed to pick stuff that actually performs like that in CFD then, and measurements later. So
Great.
just a comment.
Thank you.
Thanks. We have a little bit of time actually, because we have one cancelled presentation in this slot. So if there is an extra question.
People are trying to go back and forth between rooms though, so if we take too much time, then we completely offset
Yeah,
the schedules.
Okay, yeah, that is in fact true. But what we will then do is we will just move the two last talks one slot upwards. But maybe then Paul, and then we stop it.
Yeah, thank you. Very interesting topic. I also worked on this topic a few years back. I already talked to you about it. Just a quick question about the initialization of your airfoil shapes, because for example, when I was working on it, I think I used the NACA profile as the initial shape, and I saw that it's also quite sensitive how the Pareto front.
Yeah, we
kind of
I think
converges.
tried different scenarios. One was using NACA airfoils, and the other one was, as I said, looking into design a space, because we have always limits, right? So you say, okay, this variable varies between here and there, and then what he was doing is just randomly generating airfoils, meaning that randomly picking the values from those limits, giving it to IGP, so that we get randomly shaped airfoils. But we tried, I think, a couple of times to see the sensitivity, at least for the cases that we ran, it wasn't very sensitive. But that's one of the, I think, main things of a genetic algorithm and all heuristic maybe optimizers, is that they are to some extent sensitive to the inputs. So I think we tried it, but in our case it wasn't. That's why we just used the randomly generated airfoils based on the limits. And we just moved with that.
Thank you, and thanks again.
Thank you very much.